welcome everybody for this first of two lectures on radiative processes. Yeah, this will be a very brief, very a bit of an overview, not going into the depths of different concepts, but introduce you some of the basic concepts of radiative transfer and radiative processes. So, what kind of emission mechanisms do we see when we look out into the cosmos? And then how do we quantify those when we actually observe these and then do something with the amount of flux and amount of radiation we're getting? So the references for this, the standard reference that we always use is this by Ribicki and Lightman. Our library has it. Many of the libraries, this is slightly expensive book, but this is the standard text we always use. The second book is High Energy Astrophysics by Malcolm Longuet. This is slightly advanced, but this is also very nice, and it presents some of the mathematical derivations of some of the processes in a different way. The third book, it's called Foundations of Radiation Hydrodynamics. Although it's radiation hydrodynamics, it has a very well defined section on radiative transfer and gives you the most generalized treatment of radiative transfer, which I'll introduce in the next few slides. This is by Mihalas and Mihalas. And of course, classical electrodynamics by Jackson. So people who are from the masters, you must have encountered this book, which has quite standard for masters and also for third year bachelors, if I remember correctly. So I will be mostly taking the stuff from Ribicki and Lightman, sometimes alluding to only one slide for Mihalas and Mihalas, but just wanted to give you the list of standard references that is useful for you. Okay, so the first thing to understand about the before we go into the depths of the emission mechanisms is electromagnetic spectrum, and what part of the spectrum is actually useful for us for doing different kinds of astronomy. So you might have heard it already in this as part of this lectures. Not every frequency actually reaches us on the ground. So that there are two big transparent windows. One is optical light. We actually see everything outside from the standard frequencies that you see. And then there's radio bands. There's a large, so the brown curtain here refers to frequencies which are getting absorbed by the atmosphere outside. So at the radio frequencies, we can see things. So that's why we have radio astronomy. We can have ground-based radio telescopes which can see the cosmos. Then IR is, there are certain small windows in IR, but you have to be at a certain height. So many of the IR telescopes and also millimeter wave telescopes are actually at some of the highest mountains. And they are quite difficult to operate, but that is the price we pay because the water vapor and the atmospheres, the lower level atmosphere strongly absorbs this kind of radiations. And the high energy emission, like X-rays, gamma rays, etc., they're completely absorbed by the atmosphere. To do anything there, you have to go to space. So keeping this picture in mind is very useful for you, because then you'll understand for the different kinds of astronomy and the different kinds of emission mechanism that is giving out this radiation, where do I need to place my telescope? Now, another interesting concept that you should also have is when you observe the radiation from a physical source, what do you actually see? You end up seeing something like, so this is an actual emission of a spectrum from a quasar. Quasar is an active galactic nuclei that you're seeing light. So it's a supermassive black hole where there's accretion disk around the black hole, things matter is falling in, and there's strong radiation from the accretion disk coming towards you. And what you actually see when you actually take the spectrum, so spectrum is intensity as a function of wavelength, is something like this squiggly lines here, ups and downs, but then there's an overall trend in the spectrum. The ups and downs here, there's these sharp peaks, these are emission lines. I'm sure you're from master's and bachelor's background, of course, others more advanced. You would know what the emission lines are. You've done your lab experiments on emission lines. So when there is transition of atoms, so you kick the atom to an excited state, the electron comes down, and as it's coming down, it emits radiation. So there's emission line. And of course, you will see that the emission, although the frequency at which this transition takes place is finite, these emission lines are not just thin Dirac delta functions. They have a spread. I will not discuss about them in great detail today, but do remember that the emission lines are not just a finite frequency, but they have a center frequency and then a spread beyond the frequency. There are several kinds of mechanisms that can add to the spread. For example, relative motions of the particles that are emitting, pressure broadening, the thermal broadening, etc. And this I will not able to cover today, but remember this, that there is a spread. But overall, what I wanted you to focus on is there's a general average emission here. If you draw a red line as a mean of this emission, you can find there's a trend here. So it's a flat spectrum here up to this frequency, and then there's again a mean line. Over this mean, you have the spikes in emission. So this mean emission is something that is called a continuum. Different kinds, so emission always takes place due to atomic transitions, that is true. But if the atomic transitions are due to different processes that are emanating frequencies over a broad range of emission, radiation over a broad range of frequencies, what you get is a continuum emission. So emission distributed over different frequencies, like this. But over and above, you have certain atomic elements, metals, etc., that are excited. And that after getting excited, they make the transition down. Then you have this emission lines. So in a standard emission that you see, you have a continuum emission, and then you have an emission line. This is also true for, this is an optical spectrum from quasar. This is also true for radio astronomy as well. So for example, if you go to ALMA, you see emission from molecules. CO molecules is one of my favorites. You get a transition from CO1 to 0. But when you see the maps of CO1 to 0, you see a continuum emission. You can see the total, like a spread of the actual emission that is you're getting from a distant source. And then you also get the map of where the emission lines are. So emission lines refer to these, and the total continuum emission refer to these. Okay? So that's one concept that you must remember. And besides emission, you can also have absorption. Absorption appears something like this. So emission is when you have excited some atom, and then it makes the transition back to the neutral state, and as it's transiting back, it emits photon. Absorption is you have a neutral element in front of you. So there is an source of emission far away. There's a neutral element intervening between the observer and the source of emission. The emission goes and strikes this neutral element and then excites it, and the photon gets absorbed. And that is why you get to see depressions in the overall spectrum. So these are very well-known features. For example, again, from a quasar, you can see this is a mean wavelength of the quasar, but there are lots of individual absorption spikes, downward spikes of absorption. All of these are because these are getting absorbed by neutral hydrogen, and they are getting absorbed because they are located at different locations along the line of sight. And that is why there's a Doppler shift in the frequency at which the absorption is taking place. Another example is, for example, this, where you have absorption by a particular element, which is magnesium-2, which is getting absorbed and as the gas is sort of falling in. So there are three kinds of things you have to remember. Continuum emission, which is the standard profile. Even here, the continuum emission will be something like this, which defines the frequency, the spectrum of the emission that is being emitted. And then there is emission and absorption. Okay, now that we've gone over the basics of what actually do you observe, we'll lay down some basic foundation mathematical principles of how you characterize this emission. So this next few slides would be some basic definitions of how you define the energy that is coming towards you from the source of emission. And then we'll try to frame a differential equation to try to understand how you characterize the emission that as it gets transferred from point A to point B. So the first definition is something called the specific intensity. So you can imagine that in your image plane somewhere, you can imagine a small unit area, dA, and take the normal to the unit area. Okay? So the specific again, this is just a definition. Specific intensity is the amount of energy passing through this area per unit area, per unit solid angle, per unit time, per unit frequency. There are a lot of things in the denominator, so I'll repeat again, and this is important to keep in mind. It is the energy divided by the area, divided by the time, divided by the solid angle, divided by the frequency. So, and this is always taken as at a direction perpendicular to the area. So suppose what happens if an arbitrary area, so this is the direction of the surface, normal to the surface. But you want to find the intensity along this direction. I'm interested in intensity in this direction. So what I'll do is I have to tilt the area, the normal area, so there's a normal to the area is perpendicular to it. And then I'll use those definitions. Okay? So remember, intensity is normal to the small unit area over which you want to compute the energy flux. Then is the flux. I told the word flux, preempting it. What is the flux? Flux is the total amount of energy coming out through that particular area, through a given area, essentially. So what do I have to do to compute the flux? So flux is you take the intensity that you know at that point, and then multiply by the integrate over the solid angle. But do remember that intensity is only for the area that is perpendicular to the given line of sight. So for any general area, so for example this is the normal to this particular area, so the n over here. The solid angle d omega, as I have called it here as well, will be in this direction. So the solid angle can be anywhere. It can be over here as well, so the theta will change. Okay? So as I said, you have to reorient the area for calculating the intensity to be perpendicular to it. But instead of that, what you can do is a transformation of or a component of the area along this direction. That's why the cos theta comes in. So you have to take the fraction of the area oriented along this direction, which is the a cos theta, and then integrate over all lines of sight. So flux is the total amount of energy going through this unit area. Again, note the units. So you've integrated over the area and integrated over the solid angle. Integrated over the solid angle, the area still remains. So total amount of energy through this unit area dA, so then it becomes per unit area, but integrated over solid angle. So flux is energy by area, by time, by frequency. Okay? So that's the difference between energy, intensity and flux. Now, we will try to relate what is the relation between intensity and energy per unit volume. So energy per unit volume is total amount of energy in a unit volume. And how is it related to intensity? So let us go back to the basic definitions of intensity in the first place. So intensity, so the total amount of energy going into a particular solid angle in this way is I nu times the solid angle times the unit time dt times dA times cos theta, because theta is the angle of this particular area, so you have to take the area normal to this solid angle. So that's why the cos theta factor comes in. So this is again just from the basic definition of intensity, which is the total amount of energy into this solid angle is intensity times the solid angle times the time, area, and the area normal to it. So that's why dA cos theta. Now, what we can define is this particular region. Okay, I can just draw it here itself. This particular region, in unit time, the amount of radiation traveling through this region will actually carve a volume. So in time dt, the radiation from this travels a distance c times dt. And if this is dA cos theta, which is the area normal to it, the volume along this beam of radiation along this particular direction is c times dt dA cos theta. So this is nothing, there's nothing tricky about it. So this is the area, and c times dt is the total amount of length travel along this path in time dt. So this is the volume. So now you can clearly see that you have some expression of energy passing through this surface during the time dt. And what is the volume that is covered by this radiation in time dt? That is this. So energy per unit volume is nothing but delta E divided by dV, which we have found here. Which if you just put things in, it becomes I nu by c d omega. Do remember that I'm still calling it delta E, and this u omega is something different. So what have I done here? I have something called delta E, which is the total amount of energy passing through this surface area. I'm dividing it by the delta V. Call it capital V. Delta V is that the volume of the pencil beam along this figure is complicated. This is the area, this is the d omega. The volume of the pencil beam along this d omega. This is energy per unit volume. Now look at how I define u omega. U omega is energy density per unit solid angle. So this d omega factor is important to remember. So this is the total energy in this pencil beam. So energy per unit solid angle, because there is a d omega factor still there, hanging around there. So if we define our quantity u omega as total energy density per unit solid angle, then we can relate u omega as, this is again very important to remember because you will use this later on. U omega is intensity by c. Do remember that these are still functions of frequency. So it's I nu because it's intensity, energy per unit frequency. So u omega is also a function of frequency. So to get the total energy density, you have to integrate. So total energy density is a E per unit volume, E by V, would be integral of the u omega over solid angle over frequency. Just to keep you updated of what are the units at which we are working with. Okay, because energy units we know, it's ergs. U omega is ergs per unit volume, ergs per centimeter cube per solid angle, per steradian. Okay, so these are the basic definitions.
Integration is from 0 to 4 pi.
Integration of this one?
No, the integration range is not given. 0 to 4 pi.
Of which integral? This one? Yes. So this is the mean specific intensity. So we are integrating over all solid angles and dividing by 4 pi. If the intensity is isotropic, then this is just u omega is I omega. J nu is I omega. Okay, now with this basic definition set, we can start to derive what is called the radiation transfer equation. So to remember this, I'm skipping a lot of steps which you will find in Ribicki. For example, there is one theorem, and this can be proved, that if you are, say, consider 2 points, A and B, and you have an intensity A here, I at A, and I at B. If you have the intensity A here and there is no other source of emission or no other source that takes away emission from this ray, then the intensity at this point is equal to specific intensity at this point. Intensity remains constant along this ray. I've skipped that part. But what we really want to know is, if there are some sources here that can add energy to this radiation, or some source, as I said, there are absorptions which can take away energy from this radiation, how do we quantify it? Because that is what we want. Because suppose This is the AGN. Say suppose a supermassive black hole with an accretion disk somewhere, and this is the observer. Okay, but the emission that is coming from here may pass through other gas that can add to this or take away from this. So how do we know what is the actual intensity reaching here? So this is the mathematical derivation of this formalism. So first is, let us consider that this source here is adding energy to your ray. So then we again define some basic definitions to quantify this. So first is emission coefficient, or J nu. J nu here. So again, just note the definition and the units. J nu is energy emitted per unit solid angle, per unit time, per unit volume, and per unit frequency. Okay, so easy to just look at this equation. So dE, we know its energy is ergs. So then on the right hand side, we have J nu multiplied by solid angle, by time, by frequency, by volume. So J nu would be ergs per steradian, per unit time, per unit frequency, per centimeter cube. Okay, and if the source is isotropic, that is, you have you compute from some other mechanisms, and I'll go to the mechanisms how you do it. The power of the emission. Power means energy per unit time, and you know the power is isotropic, so there is no directional dependence. So energy per unit time, per unit frequency, we know. Then J nu is just 1 by 4 pi this quantity, because J nu should be per unit solid angle. And since the power is distributed everywhere isotropically, it's just 1 by 4 pi. Why I'm saying this? Because when you actually try to compute different kinds of emission mechanisms, this power is something that you can readily compute by looking at how electrons are moving around and how the charges are radiating. Once you know that power, you can easily get the J nu. Okay? So then, let us try to relate this. So now we have an expression of E, the energy, relating it to the J nu. From our definition of intensity, we already know how intensity is related to energy. So suppose something happened here, it changed the intensity. And that change in intensity is di nu, small change in intensity. And that also resulted in a small change in the energy being added to the beam. So just from the definition of intensity, delta E is di nu d omega dt dA d nu. You'll hear this so many times, you'll remember by the end of this lecture. This is equated to here, J nu d omega dt d nu dA ds. You just equate this, you get the first relation, which is the small change in specific intensity di nu is equal to the J nu times ds. What does this mean? Now remember, J nu is per unit volume. So this, I'll redraw this part. It's a big volume element here, and each point here has some J nu. It can depend on space. It can also depend on time. I'll come to the temporal change soon. But let's say that everything is static in time, but it's changing in space. So your small ray is covering small elements here. These are, let's say, ds, ds1, ds2, etc. So the small change in intensity after it has traversed a small length here is di is J nu ds1 di1. So to find the total change in intensity, you just integrate it over this entire length. So from a volumetric definition, you are going to a per unit area. That is the important thing. Because J is per unit volume multiplied by length, and I integrate, you again get something per unit area, and that is what the intensity is, energy per unit area. Next is absorption. So again, this is a basic definition. What is absorption? Absorption is when you have photons coming and streaming through a medium. It goes and hits the elements inside the medium. Now this can be atoms or molecules in their neutral state. It can scatter, or it can get absorbed. So there's a finite probability of that happening. So that this is all that we quantify in this way in terms of definition. So a fraction of the energy can get absorbed as it is passing through this medium. So we quantify it as delta I nu, which is this fraction of energy that is changing of the specific intensity, is alpha nu times I nu times ds. Again, this is just the way we define this quantity alpha nu. And alpha nu is called the absorption coefficient. Now again, pay close attention to the units. On the left hand side, you have the specific intensity, all the energy per unit time, per unit area, etc., etc. On the right hand side, you again have intensity, so you don't have to worry about all the other factors. Look at this alpha nu and ds. So you just have a unit of length here, so alpha nu has to be per unit length. This is important to remember because alpha nu is closely related to absorption cross section, sigma, but sigma is per unit area. So do not mistake that absorption coefficient will also have centimeters to the power minus 2. And I'll come to exactly how they're related. But this is how we define the definition of alpha nu. So now again, let us go back to our basic definitions of intensity in terms of the energy. So suppose there are n particles here. So n is a number density of the particles. And again, consider this pencil beam along this ray with the area dA and a distance ds that it covers. So the total number of particles is just n times this volume. Volume is the area times this distance, dA times ds. Okay, and then again, we have to find out what is the intensity per unit solid angle. So to keep in mind that we have to consider a solid angle along this pencil beam, which is the d omega. Now, suppose the fraction of energy that is absorbed is delta E, and that corresponds to a small change in the specific intensity, which is di nu. So again, going back to our basic definitions, di nu, dA, d omega, dt, d nu. This now we have to equate with actually what is the microphysical process that is absorbing things. Now this is where the absorption cross section comes in. So with each of this particle, there is associated an area over which the absorption process will take place. Now this again becomes a probabilistic definition, and I'm not going into how it is a probability because I'll go to the optical depth soon. But suppose that within this cross section sigma, around each particle, the energy is absorbed. So what is the total amount of surface area being presented by these particles? This is n times the number of particles times this n, sigma. Okay, and what is the volume of this potential blocks of absorbing regions that is being presented to this ray? This times ds. So this multiplied by the I nu is what is actually giving you the absorption. So this is the initial incident energy, incident intensity. That is getting incident or falling on these small pellets of volume here, and anything in this volume will get absorbed, let's say. So that is the physics. How exactly the absorption comes in, again you have to go back to the microphysics of it, which I may not cover here, but you have to consider that atomic transitions and what is the mean area over which the absorption is taking place. But this sigma can be found from actual experiments. So once we know this sigma, we know what is the volume being absorbed, then these two equations are pretty trivial. So once you put them in, you have d I nu is minus n sigma I nu ds. I'm quoting here minus because the energy is getting absorbed. That's why the negative sign here. Now compare this with the basic initial definition of what the absorption coefficient was. So alpha nu is nothing but n times sigma nu. Now n is a total number of particles, number density of particles, nothing related to mass so far. Total number of particles per unit volume. This multiplied by the absorption cross section or the cross section of interaction, let's say. It can be also scattering. N sigma. Scattering is a different beast. I will not go into it, but you are welcome to read Ribicki for that. So alpha is n times sigma. Again, look at the units. N is per unit volume, so centimeter to the power minus 3. Sigma is centimeter to the power minus 2. Yeah. The sigma is this should be square, right? I should change my notes. Centimeter square. So multiplied, you get centimeter to the power minus 1. So that the units check out. Some papers in textbooks refer to this absorption coefficient as per unit mass, which is the kappa nu, and just note the definition here. So now that we are equipped with what is the change in energy through this ray as it is passing through this volume, we can write out this equation. So to get to this equation, note what we derived in the previous slide, which is di nu is equals to j nu times ds for the emission part, and minus alpha nu I nu ds. It's absorption part. Take ds on the numerator, on the denominator, and you get this equation of the radiative transfer along a particular ray, which is di nu ds equals to j nu minus alpha nu I nu. I'll just go through this slide and then I'll take questions if you have any. So far, we have assumed that everything is time independent. What happens if things are changing with time? I will not go through the derivation of this. You are welcome to read Mihalas and Mihalas for this, and this is a very nice book. But the time-dependent radiative transfer equation looks something like this, which 1 by c del I nu del t plus this standard equation that we have derived just now. Okay, now then the specific intensity, the emission coefficient, and the absorption coefficient all become function of time. Now note that this is along a particular ray, but in a physical space you can choose to work in a own system of coordinates. Suppose you are working in a Cartesian coordinate system, so then the derivative along a particular direction you can just break it down in terms of the cardinal axis. So del I del s essentially is del I del x times del x del s and so on. But these quantities are direction cosines of this ray. So let me jot down a line. You may never actually require this, but it's good to know this information. So suppose you want the radiative transfer along this line S. This is theta. This is phi, x, y, z. Okay. So then these quantities, this particular line is often denoted as nx, ny, nz, which is the direction cosines, which essentially gives you the angle the line makes with each of this cardinal axis. And these derivatives here, del x, del s, del y, del s, del z, del s, they are nothing but this direction cosines. So after a few adjustments, you can turn this derivative into something like this. The direction cosine times the gradient along this particular direction times I nu and j nu minus alpha I nu. This is the fundamental equation for time-dependent radiative transfer. And once you go to radiation hydrodynamics, you have to solve for the fluid dynamics equations along with radiation as a fluid on top of it. And that is why this is given in the book on radiation hydrodynamics by Mihalas and Mihalas. So it's not linear in the sense that a fraction of the energy is getting absorbed. Internally it can have different microphysical processes. So essentially what you see, there's a photon flux. A fraction of those photons will get absorbed. There's no reason for it to be non-linear in that sense. Unless you go to a different method of absorption, suppose you go to a refractive medium, then the story changes. Okay, but if you just assume that I'm throwing 100 photons onto it, a fraction is absorbed, that is the basic definition. Okay, Any other question? Okay. So then let us discuss some of the basic solutions of these equations. So the first is, and let me write down the equation again. di nu ds is equal to minus alpha. I'm dropping the new subscripts, but do remember these are functions of nu frequency. Minus alpha I nu. Okay. So there is no emission, just pure absorption. Simple equation, you integrate it, you get an exponential function like this. So I have dropped the J nu term. Get exponential solution like this. So what does it mean? Suppose this is a surface. And then outside the surface there is no medium. And then as soon as the ray comes and hits this surface, there is density. So density is 0 outside and starts from here. So suppose it's all background uniform density here. So the intensity up to this point before it hits the surface is constant. Intensity same here because there is no absorption or emission. As soon as it enters the surface, the intensity attenuates exponentially. And that is given by exponential minus tau. I skipped one term here, which is the definition of this quantity called tau. So if you look at this integral here, the solution to this equation, you get an exponential alpha times ds. So it is the depth from which we are calculating things. So I'm now calling the ds starting from this 0, which is z equals to 0, let's say. So anything below z equals 0 is ds. So this quantity, integrating alpha times ds from z equals to 0 to some value z prime here, z prime, but this is integrated along this ray. Okay, this quantity is called the optical depth, which is tau. Now truly if we have the optical depth from one part to another, this should be tau 2 minus tau 1, but since tau 1 is 0, I'm just calling it tau. So do remember this definition, which is called the optical depth. You can also write it in the differential form, which is d tau nu is alpha nu ds, small change in optical depth as you traverse different parts of this ray. So if the simple system alpha is constant, you get an expression something like this, which is the intensity at this point here is equal to the intensity at the surface at z equals 0 multiplied by this exponential minus tau, exponential of minus of the optical depth. And optical depth is integral of alpha times this distance here. So if the tau is greater than 0, so if your absorption coefficient is such that your optical depth is more than 1, you have a function which is exponential minus some positive quantity, the intensity drops drastically. It's exponential decrease in the intensity. And that is called optically thick. So this is an important distinction here. What is optically thick and what is optically thin? Because we'll come back to again what are the properties of an optically thick medium. If your optical depth, if your alpha and ds is such that the tau is not greater than 1, tau is less than 1. So suppose you are passing through this, let me come back to this one. You are passing through this medium here. There is some alpha, some absorption here, possibility of absorption, and some line here. So now you calculate the optical depth, which is tau equals to integral along this particular length. Alpha times ds, approximate alpha times L. Put in the value of alpha, put in the value of L. If tau is less than 1, then the intensity does not change much. As soon as this alpha times L, if alpha is a constant, then as soon as you increase L such that tau becomes equals to 1, from then on, the intensity starts to drop. So what will happen is, the ray will go on here and then will stall here. Anything behind it will not see the intensity coming from here. Okay. Next is, so now we know how to solve the equation for alpha for just absorption. Let us try to solve the equation for the full transfer equation, which is we put in J nu as well. This requires some steps, so I just illustrate it here. I'll do this and then black body and then end for today. So the full transfer equation looks something like this. Again, I'm dropping the news. Do keep in mind that they are all function of frequencies. Oh, this is how it looks, right? So next, what I'll do is I'll divide everything by the alpha. Now this we know, this is d tau. This I will call a different function called S. So my new equation S minus I. So now what I've done, I have gone from the path length being the variable over which we do the integration to the optical depth, d tau. Again, the optical depth itself is integral over the path length. But going to the optical depth space helps us in evaluating this integral more easily. And more importantly, I've introduced a new function called S, which is the ratio of the emission coefficient to the absorption coefficient. That is called a source function. And again, you'll clearly see now what is the relevance or implications of source function. Now, this integral can be integrated quite trivially using the integrating factors. I'll not go through the steps directly, it's outlined here. You multiply e to the power tau nu everywhere, and then you can form the integral, and then you get this result over here. It will be there in the PDF, so don't bother working it out right now. Now, let us note the limits of what is happening here. Let me use this itself. So what I'm doing here is going from point 1 to point 2. The optical depth at point 1 is tau 1. Optical depth at point 2 is tau 2. I have the intensity at this point as I tau 1, and intensity at this point is I tau 2. What I want is, my boundary condition is the intensity at point tau 1. I know this value here. Okay? I want to evaluate intensity after it has traversed a path length S and reached a point 2. That is what this final solution gives us. And we know that in between there is a source function, which is function of tau prime. Tau prime is changing between tau 1 and tau 2. Tau prime is the integrating variable here. So the final solution gives you I nu at tau 2 is equals to I nu at tau 1 multiplied by this exponential, which is tau 2 minus tau 1. So essentially, the difference in optical depth between point 1 and point 2. So it's a different. Yeah. I at tau 2 equals to, I'll come to the next part later, but let's understand what this means. I at tau 1 times exponential minus tau 2 minus tau 1. Okay, plus the added factor. Come to that later. So the added factor is an integral over the source function. Source function is J nu by alpha nu. Let us see if our first example can be recovered. Suppose we have no emission, only absorption. Source function is 0. That integral goes away. So I at tau 2 is I at tau 1, tau 2 minus tau 1. if again I define tau1 as the starting point of the surface, so optical depth tau1 is 0, I recover this solution, which is I exponential minus tau. Minus tau. So we are fine. Next, the complications come when we have emission along the line. Then we have to understand what this, evaluate this integral. Evaluating this integral in actual physical scenarios is extremely complicated, non-trivial, because your emission coefficient is a function of space. Absorption is also a function of space. So this can be evaluated for certain idealistic situations, for example, but it's quite complicated, and there are approximate solutions of this for different scenarios. I'll not go into that. But let us do one particular case where tau2 minus tau1 actually goes to infinity. So this quantity, let's say tau1 is 0, we are starting from the surface, and the tau2 goes to infinity. Okay, and then let us suppose that the source function is just constant. It is not varying with space. So what do we get here? If we just evaluate this integral, tau1, tau2, source function, exponential minus, that's what it is, right? Tau2 minus tau prime, d tau prime. Okay, tau2 is just constant, so we'll take it out of the integral. And s is also constant, so take it out of the integral. So exponential minus tau2, this is equals to s, then this integral, e to the power tau prime, d tau prime, tau1, tau2. Okay? Evaluate this, you get s times e to the power minus tau2, and then e to the power tau2 minus e to the power tau1. This just cancels out, this is just s minus s times e to the power minus tau2 minus tau1. Okay? Now I'm assuming that tau2 minus tau1 is infinity, which is the optically thick limit, or tau2 goes to infinity. So we are deep, so if this is the surface, starting point of the surface, and a ray is coming like this, we are deep inside the surface. So this term vanishes. The first term also vanishes. Okay? So what we are left with is I nu equals to the source function. So for an optically thick system, where you are deep inside the system, it is optically thick, the intensity is the same as the source function at that point. Now this is important to note because this is what we'll use for a black body. Last 5-10 minutes. I hope this was clear. Any questions? Okay, good. Last 5 minutes. Basics of black body thermodynamics. Now you're all from third year bachelor's and master's, so I'll not go into the details of black body radiation, but what I'll try to connect here in this lecture is connecting black body thermodynamics to the radiative transfer equation. So we all know black body is when the radiation is in equilibrium with a thermal body, and the thermal body is characterized by a temperature, and the radiation is in equilibrium with it. You can derive the nature of the expressions of the energy density of the radiation using the standard arguments of statistical mechanics, so thermostatistical physics. But let us first again make some definitions of black body radiation. So radiation, intensity of the black body, we'll call it as B nu. I nu equals to B nu for a black body. Let's just call it first. Now the object is in thermal equilibrium. So deep inside, there is no change in the intensity. So what is happening here? I just showed that if there is no change in the intensity, the radiation, the radiation inside for a black body completely loses any memory of what is the radiation outside. So deep inside the optically thick medium, I equals to S, and if the optically thick medium is in thermal equilibrium and the radiation is in thermal equilibrium with the optically thick medium, this is equals to the black body radiation. So for a black body radiation, the specific intensity of the radiation is equals to the source function. So the radiation is in thermal equilibrium with this optically thick medium. We know the source function of the optically thick medium because that is the property of the microphysics of the medium itself. And if the radiation is in equilibrium with it, then we have this. So then let us go back to the definition of the radiative transfer equation. For a black body, the radiation is not changing. So no matter how much you go along the ray, if it's deep inside the system, is thermal equilibrium, d I nu d tau is 0. What does that mean? So my transfer equation was d I nu d tau equals to j minus alpha I. This is equals to 0. Okay. So then j by alpha equals to I. Again, from the basic definitions. So this is called the Kirchhoff's law. I we know as the black body function, or the black body specific intensity. So the emission coefficient is equals to the absorption coefficient and the black body. So whatever is being absorbed is also being emitted back. So the intensity along that ray is not changing. That's the basic concept, the physical concept of black body radiation. Kirchhoff's law is very powerful. We can readily use it to compute one quantity if we have the other. Black body B nu function we know. I'll come to that in the next slide. Suppose we can find out what the J nu term is, okay, which is the emission coefficient of a thermal system. We can immediately evaluate what the alpha nu is. Now note that the absorption that it is doing, it does not need to be a thermal radiation impinging on it. It can be a non-thermal radiation, and I'll come to the examples of non-thermal radiation, but the material that is absorbing, that is a thermal material. So although the incoming radiation may not be thermal, the absorption process is due to a thermal material, and that is why we can use Kirchhoff's law to immediately evaluate what alpha nu should be. So once we know J nu divided by the black body function, we get the alpha nu. Very powerful law. And then we have Stefan's law. Not go to the details, but I've sketched a derivation of how you can derive it from the first principles of thermodynamics. That the radiation density is a function of temperature and scales as A, which is the radiation constant, and temperature to the power 4. Again, you're all very familiar with this, I'm sure, but this is how you can sketch it from the first principle, from the first law of thermodynamics, assuming a radiation fluid. Now, we have derived in the beginning of the lecture a relation between the energy density per unit solid angle and the intensity. Now remember this B nu function that we're talking about here, that is the intensity of the black body radiation, specific intensity of the black body radiation. From statistical mechanics, physics, we can find out by different methods. Planck used something, you can use something else. This expression, which is the energy density per unit solid angle for a black body radiation field, which is 2 nu square by c cube h nu by exponential h nu kt by minus 1. This is E omega. In the beginning of the lecture, I showed how E omega is related to the specific intensity as I by C. Then if this is a black body radiation, we can immediately get the black body function, which is B is a function of 2h nu. So essentially just take C here, and B is 2h nu cube by C square. So this is all it looks very trivial, but it naturally comes out from the basic definition of black body. Now consider these two limits when the frequency is such that h nu by kt is less than 1. So the energy of the photon that you are considering at the particular point in the black body spectrum is much lower than the thermal energy. Then you can approximate this expression as, you can forget the exponential part, as 2 nu squared by c square kt. B nu is 2 nu squared by c square kt. The other limit is called the Wien limit, but the energy photons are highly energetic. So h nu by kt is greater than 1. Then again, you can ignore, you can expand the exponential here, and you get a linear function with an exponential quenching. So the function will look something like this. At nu less than kt, it's almost linear. If I just go, it's already there. It's almost linear. So this is the Rayleigh-Jeans part. But beyond this kt, beyond the turnover point, then it exponentially gets quenched, and that is the Wien part. Okay, and this is how the blackbody radiation looks like. And as you must have already known, the peak of this distribution gives you the Wien's law, not law, but just a relation, which is h nu max equals to 2.82 kt. Do note that this is the Wien's relation with respect to frequency. If you transform the blackbody function in terms of wavelength, lambda, and then take this, well, essentially what I will do is recast b nu as a function of b lambda, then find the peak of this function db d lambda. This relation will be slightly different. The front coefficient will be slightly different, which goes to show that this is not really truly a law, but where the energy peaks. This is a very one of the most well-tested blackbody spectrum, which is the CMB, and this is actually experimental verification the CMB is a blackbody. Okay. Last thing I wanted to show today was this definition of brightness temperature, because this is a radio astronomy school, and I'm sure you'll come across this definition in many contexts. So in radio astronomy, we are dealing with photons that are less energetic compared to the temperature of the system. So we are usually restricted to the Rayleigh-Jeans part of the blackbody spectrum. Now, using the basic definition of the Rayleigh-Jeans formalism, let me go back to here. We can define for any incident intensity or any incident radiation, we can find a specific intensity. We can assign a temperature to it. So no matter whether it's actually a thermal radiation, we observe the intensity here, and we can just ascribe or empirically characterize it by a temperature here, and that is called a brightness temperature. So what is the effective temperature associated with the brightness? And that's how you can call it the brightness temperature. Do remember that brightness temperature may not necessarily reflect the actual temperature of a system, because the basic assumption of this is this radiation is actually a thermal radiation from a black body. What if it is a non-thermal radiation? Then the value of the brightness temperature would be very different and large actually compared to what your standard temperature of the object would be. But this is just a easy way to characterize the temperature. And again, so what you do here is you get the brightness temperature, you recast it in terms of the wavelength, because it's easier to work with when you're doing radio astronomy. And you take the flux and divide it by the beam, because I nu is the intensity per unit solid angle. So this is the beam size of the radio antenna that you're using, and that is how you define the brightness temperature. Do note that if you now go to the radiative transfer equation here, and let me go back one more slide. Yes. So B is linear with T. You can recast the transfer equation in terms of the brightness temperature now. Okay. So this is how it looks like. d tau nu is minus TB, which is the because of the I nu, and plus T. T is if it's the source function is actually thermal. Okay, so you can ascribe a temperature to the source function, and the source function is thermal, you get T. Now again, standard solutions looks like this. If it's an optically thick system, tau is infinity. The solution reduces to such that the brightness temperature is the actual temperature of the system. So this is quite neat, that if your temperature that you're measuring is truly a temperature of a physical object, then you're okay, and that means that this is optically thick medium, so it is a blackbody radiation. In typical systems, for example, synchrotron radiation from jets, you find the brightness temperature orders of magnitude higher than what it should be. So suppose you get a radiation, you get a brightness temperature 10 power 4. Now it means that the plasma that is there, it can have temperature 10 power 4 Kelvin. And if you photoionize it with radiation from different sources, the standard temperature is actually 10 power 4. So if you measure brightness temperature of that region, you can get a hint that, okay, this may be a thermal radiation that we are seeing. We need to characterize its spectrum, plot it, etc., to understand what this emission corresponds to. Now suppose you are getting a brightness temperature 10 power 12. That it cannot be a standard thermal system. From basic physics argument, the amount of energy that you require for it to be such high temperature will be extremely large. So what that means is the basic argument of defining a brightness temperature is incorrect. But nonetheless, it gives you some measure of what is the type of radiation you're getting and what is its brightness temperature. So next lecture, I'll go into some of the details of overview of the emission mechanism. So I will stop here today.